Okay, the earliest known applications of integration was done by a Greek mathematician called Eudoxus, who used what is today called the method of exhaustion in order to calculate the area of a circle. It wasn't very easy to calculate the area of a circle back in those days during the Greek civilization because they didn't yet have an agreed upon formula like we have today in order to calculate the area of a circle. And so, what Eudoxus did was, inside a circle, he constructed 4 points at equal distance from each other so that we got a square inscribed in a circle. He found out the area of the square, and then, of course, the area of the square will be the side of the area of the circle would be the side of the square divided by 2 times the side square. So, and then you bisect the arc and so AB, suppose this arc is AB, you bisect the arc and you join the line segments over there also, C. And then this arc you bisect it further and you join that as well, and keep on finding the area of the resulting polygons. And so for arbitrarily large values of the sides of the polygon, you come closer and closer to the actual value of the area of the circle. So this is called the method of exhaustion. It was well known to the mathematicians of the day, and it is basically speaking a method of integration of the areas. And so this method, even though it is not a general method, it is not specifically integration, but it is an application of integration, and that is why it is counted as one of the earliest evidences of the applications of integration by humankind. Apart from that, Archimedes, a few years after Eudoxus, also used, and he refined the method of exhaustion to calculate the area of the circle, the area of a sphere, the volume of a sphere, area of a paraboloid, etc. So since Archimedes refined the process of the method of exhaustion, he was able to calculate the areas of more complex figures than just a circle, like a paraboloid, a parabola, sphere, volume of a sphere, and so on. So this was a further development in the discovery of the formal process of integration. And then at the same time that around Archimedes, maybe a few hundred years here or there, maybe in the 2nd or 3rd century of the new era, there were Chinese mathematicians called Liu Hui, and there was a father-son duo of mathematicians called Zhu Chongzhi and Zhu Geng, who also independently found out a way to calculate the area of a circle. And then in the Middle Ages, there was Bonaventura Cavalieri, who discovered a method of integrating x to the power of n, where n is a constant and x is the variable. And so this was a significant step towards generalizing and formalizing the process of integration, because before this nobody had done the work. And then there was a few hundred years where there was no development for 500-600 years, 700 years. And then came Isaac Barrow and Evangelista Torricelli. These guys were mathematicians and theologians in the 17th century in Europe. Isaac Barrow, in fact, was the professor of Isaac Newton. He was, at that time, at Cambridge University, what is called the Lucasian Professor of Mathematics. And Isaac Newton was Isaac Barrow's student. So Isaac Barrow and Torricelli, independently again, because in those days they had very few methods of communicating with each other, independently discovered the connection between integration and process of differentiation. But then again, even these guys had not really formalized and brought together all the different mathematical concepts that go into integral calculus, and differential calculus. And for that, we had to wait until the next generation of students of these guys came in, and those were the great Isaac Newton and Gottfried Wilhelm Leibniz. And so Isaac Barrow could only write a crude proof of the fundamental theorem of calculus, and another English mathematician called John Wallis generalized Cavalieri's method of integrating x to the power of n. But then the formalization and the development of differential calculus and integral calculus, and also the understanding and the interchangeability between differential calculus and integral calculus, and the complementary nature of differential and integral calculus, was discovered independently by Newton and Leibniz. There was a debate for many years in Europe as to who had discovered it first. It so happens that Isaac Newton had discovered it first, chronologically speaking, but then Leibniz published his results immediately after discovering them, whereas Newton kept his findings hidden. He was a little insecure about his work, and so even though he wrote all of this and kept it well hidden inside his safe, he had written the dates for when he wrote down all these notes. And based on that, we know today that Newton had discovered the calculus principles first compared to Leibniz, but then Leibniz was the one to publish it before Newton. So this was a little bit of how integral calculus came to be developed. It came to be developed in small steps. And of course, the development of integral calculus does not end with Leibniz and Newton. It just begins with Leibniz and Newton, because in the 18th century and in the 19th century, there were great mathematicians like Leonhard Euler and Bernoulli and Kurt Gödel, Hilbert, and the later developments of integral calculus were done primarily by Euler, another German mathematician called Gauss, and Bernoulli, of course, the Bernoulli brothers. So that is a little bit about the history of integral calculus.